Good evening, everyone. I'm Arlene Baxter. Tonight is my tremendous pleasure to welcome someone who we are taking advantage of the fact that he's actually not here in person. We thank Dr. Glyn Collinson for staying up late. He's on the East Coast. I had the pleasure of meeting him in person when he was here in Berkeley briefly, and got to sit side by side with him and really experience in person his tremendous passion for his subject, which is rocket ships. We hear that phrase so often used casually, oh, it's not rocket science. But in fact, that is exactly what he does. He has a long history of being passionate about rockets, and you will see very soon just how far back that goes and why it is that instead of my doing the moderating of questions, they will be moderated later by Dr. Kurt McKusick, one of our past presidents, and you'll see why in just a moment while that's so appropriate. Glyn Collinson got his master's degree in physics from the University of Bristol in the United Kingdom, and his PhD in space science from University College London. Since 2010, he's worked at NASA's Goddard Space Flight Center, and he's one of a handful of scientists who build spaceflight hardware and do scientific research with data sent back. Tonight, we're going to be hearing, I think, a fascinating topic about what makes the Earth habitable. And with that, it's my pleasure to turn it over to Dr. Glyn Collinson. Welcome.
Hello. Yeah, I want to talk to you a bit about my rocket ship and all this stuff. So I guess the story really begins when I was 12, when my godfather, Kirk McKusick, who many of you know, bought me a model rocket kit whilst visiting my family over the summer in North Wales. He had to convince my parents that this was indeed a safe thing to do. And these are pretty cool. They're actually real rockets. I mean, they have solid fuel. You can burn things with them if you're not careful. So they're just like the real thing because they are the real thing. So here I am. This is our very first rocket we built together. And I vividly remember the day that we launched this thing. And that's the first takeoff of our very first rocket. And I just remember the excitement that I felt watching that rocket that we built disappear off into the sky. I think I just completely lost my marbles. And this was so much fun that every summer we would plan a new rocket, which got bigger and bigger. In fact, and we found a G&K rocket yard, the logo of which I even managed to find. And today, basically, things are continuing. And so this is my rocket. This is actually just the space. This is just a piece of it built at NASA Wallops flight facility on the East Coast. Here, you get a sense of the scale of the thing. So this is me by the top part. So if we look at the map sort of above, this is really only this is what's called the payload, but this is basically the rocket ship, or this is a spacecraft. So the cylindrical thing at the bottom, this is like the service module. So it's got the batteries, the computer, the radios, ACS, attitude control system, cold gas argon thrusters inside. It has, it goes up. And then all the things in front, which are all of this spidery stuff all folded away, those are the scientific instruments, which will all pop out and deploy. And in flight, they're covered by this nose cone, which will sort of pop off like a cap off a pen. And it's to get it to space, we're launching on this enormous 3-stage rocket, this solid rocket. So I am going in just a month or so to this place. This is Nyalesund in Svalbard. So it is essentially an island off the north of Norway, basically the most northern rocket base up there. And the science that we want to do can only be done from there. So we're going to fly there. And this is what we're going to do with it. We're going to launch from Nyalesund. Here you see there's Greenland, the polar caps up there. And we're going to go basically straight up to hopefully about 800 kilometers. And we'll splash down somewhere in the Greenland Sea. So Endurance is basically an unguided ballistic missile. The unguided part of what makes it a peaceful scientific spacecraft. So there's a 65% chance it will land somewhere in this inner bullseye, a 90% chance it will land in this second bullseye, and a 99% chance that it'll land in the within there. So it's going to come down somewhere in there. Why are we doing this? So essentially, I've been driven through a lot of my career in space science, in building machines to go to space. to try and help understand a little bit about why we're here. What is it about this planet that makes us habitable? Can we use that to extrapolate lessons for all the other planets? That we can say that two fundamental things that we think are quite important are, well, we have this atmosphere that we can breathe. So you definitely need a temperate atmosphere, not too hot, not too cold, and with oceans of water. Right? Very important. We've got to have liquid water on the surface. I think we're agreed on that. So how does a planet have an ocean and temperate atmosphere? How do you do that? So essentially, the deal is this, that now, of course, what I'm about to explain is very sort of reductive, but fundamentally, planets generate energy fields, and you want these fields to be in balance. If that is complicated, so don't worry, it's not complicated. So one energy field, gravity, the force of gravity, which holding you down. So it's what's holding you down to right now, but it's also, if you think about it, what is holding the atmosphere on. So good, you want to have some gravity to hold on to your atmosphere. That's good. And another energy field you've heard of, the magnetic fields. Some planets generate them, others don't. Ours does. And it looks kind of like this. It's basically Earth is basically a big bar magnet. A dipole field is what we call it, the two poles. So it's a big magnet. And sort of the story that everybody's told, sort of the lie to children, as it were, is, well, a magnetic field is good because it shields us from the solar wind. And well, that is true, but it also acts as this enormous collecting area for the energy from the sun. And all that energy just gets funneled down the magnetic field lines into the poles. So it's actually the role of the magnetic field. We know it's important, but that's actually a really hotly debated thing right now. And how this all kind of works, right, is open debate. So, but there is a third field, which I'm here to talk about tonight, and it's sort of an electric field. Okay, now there's electric fields everywhere in space. So let me just back up. So something that you've experienced. So if ever you've gone to your laundry and you've pulled out a sock and all the other socks have been like, we're coming too, and they all kind of stick together, that is the electric field that is doing that. You've experienced that there. That's what's sticking the socks together. So there's electric fields everywhere in space, but I'm talking about one very specifically, where it's called, jargon coming up, the ambipolar electric field. And so to describe it, it's kind of just as Earth's core generates the magnetic field, the top of the atmosphere generates this ambipolar field. Think of it like the force. It surrounds the ionosphere, the atmosphere. It penetrates the ionosphere, it binds it together. So at the top of the atmosphere, the ionosphere, it's all at the top. It all gets broken down into ions and electrons. So the atmosphere at the very top, the ionosphere, it's composed of basically the same elements as we breathe down here. So there's oxygen ions and there's nitrogen ions, there's these other things, and the electric fields can help push these ions off into space. And you can imagine, if you lose too many of these oxygen ions, so without them being replenished from within the Earth, then quickly you'll end up with nothing. Right? So these are sort of the three fields that we're going to sort of talk about. Let's do some examples here. So here we're going to talk about, let's do some actual case studies of planets here. So there are 4 rocky planets in the inner solar system. Innermost Mercury, which today is not appearing in this film because no atmosphere. But we're here to talk, let's talk about Venus, Earth, and Mars. So obviously, I'm sure you're familiar with the idea of the Goldilocks zone, where you might have liquid water on the surface. And there's this classic thing of, well, Venus is too hot and Mars is too cold and Earth is just right. But the truth is more complicated than that. There's lots more going on. So to really try and understand this, I'm going to take you to one of these planets right now, very quickly. So I'm going to take you to Mars right now. Let's go there, but not the Mars that you may be familiar with. This is Mars as it was about 4 billion years ago at its very early history. A much more pleasant place than it is today. You could basically walk around on the surface with a simple breath mask. You couldn't breathe the atmosphere. It's a carbon dioxide atmosphere, but it was at least, you think, like, twice as thick as Earth today. And it had a lot more water than, it's difficult to estimate. So I've worked on this mission here, the Maven mission to Mars. And the mission was tasked with trying to get answers to this. And though it's difficult to get the water inventory, at least 7% by volume of the amount of water that Earth has today, right? So 7% of Earth's by volume today. And it doesn't sound like a lot, but remember, Mars is a lot smaller. And if you took all of that water that was then, and then you covered it evenly over the whole planet, everywhere would be about 500 meters deep in water. And obviously it wouldn't do that, right? Earth, it would have some places would be deeper, some places would be mountains. So there would be quite substantial oceans. And we know that because of the geology from the Mars rover. So we know it was a much more habitable place. So let's check in with those energy fields. The gravity field, number one, the gravity is about a third of one Earth, right? 1G, right? A third of Earth's. And interestingly, we know it had a magnetic field. And again, this dipole field, like remember the bar magnet. So it had this bar magnet kind of field. So we have this nice, habitable, lovely place, but not so much today. So here we are, in the present day, most of its atmosphere is gone. Pretty much all of its water is gone. What little is left, I think there's a third of a percent of Earth, and it's mostly in the polar ice caps. In fact, you can, but this is here. I was telling you about the evidence of wetter times. This is from one of the older Mars rovers that NASA sent from JPL, and you can see this. And if you can see the striped rocks, those are sedimentary rocks, laid down with water. It is a true fact that the magnetic field is gone around the same time of the oceans. If you remember, there's that third field, that electrical field we wanted to talk about. So I was actually involved in the team of trying to measure this field at Mars, and we measured it. And if you add it all up, it generates about 0.7 volts of energy, right? And that's nothing, right? I mean, that's about half of a watch battery. It's absolutely nothing, but that's enough energy to actually give oxygen ions about a third of the energy they would need to escape to space. Now, I should clarify, thanks to Maven, we actually think that the electrical field, it definitely played a role in the loss of the atmosphere, but probably not a dominant role. Thanks to Maven, we can actually explain a lot of what happened at Mars very simply with this first field, the gravity. Very simply, the planet doesn't have enough gravity. It doesn't have a magnetic field to shield it, so therefore the solar particles bombarded the atmosphere, and a lot of it was stripped away. Some of it went down, and the rest of the ions. This helps. So, but we have our data point. Let's head to another planet. This is Venus. Very, very different place. So the air pressure there is about 90 times that on Earth. It's like being deep under the ocean. So tons of atmosphere. But the one thing it doesn't have is water. So you may know that the surface of Venus is so hot that it can melt lead. This is a real photograph, by the way. I didn't have a photograph of 4 billion year old Mars, but everything else is real photos. This is taken by the Soviet Venera lander, or one of the landers in the 1980s. And this is sitting in this balmy temperatures. And of course, you could never have liquid water on the surface of these temperatures. That just boils the water away into steam, but the atmosphere still is very dry. So where did it go? So let's look at the energy fields, right? Well, for a start, the gravity field is actually pretty similar to Earth, right? A little bit lighter, but not much. No magnetic field. That's interesting. I was the lead author in the paper that made the first measurement of this planet's field. And to our shock, we found the potential to be 10 volts, right? If remember, we were just at Mars with 0.7. This is enormous. And in fact, even with the strong gravity of Venus, it's more than enough all by itself to pull oxygen out of the atmosphere. So if that was a lot for you, let me say it this way. Imagine that you are an oxygen ion, which is now floating around in the top of the ionosphere of the atmosphere of Venus. You have lost a terrible lottery because you have this monstrous electric field that will suck you out into space. Let's go to a wet one, which is we're all familiar with, especially if for those of us who have managed to venture under the seas. So gravity field is quite Venus-like. We have our dipole magnetosphere, right, that bar magnet. I hear you cry. What is this electric field? Where is this thing set? Well, we think it's actually pretty weak, maybe only about a third of a volt. And with the stronger gravity, you can see that's about. We've been sort of comparing how much energy does it actually provide to the oxygen. Well, not very much, pretty minimal. So, and this is of course incredibly reductive, and planetary, atmospheric loss is really complicated. But if you want to understand how planets work, you kind of want to know where the main dials are set, right? And it's kind of an interesting fact that on this wet planet, we have a very weak electrical field, whereas on Venus, this dry planet, we have a really strong one. So it would be, obviously that's kind of an interesting, idea, and we'd love to investigate it further, but there's a problem. And the problem is the question mark after that 0.3 volts, because you see, it has never been measured. It's so weak that until recently, we didn't have the technology to go and measure this. Now, we had thoughts, but the technology didn't exist until now. And that is the goal of Endurance. So that's under PI of this rocket mission, Endurance, and we have a focused goal to try and make the first measurement of the magnitude and structure of this electrical field generated by the ionosphere. So that was a lot of science that we've gone. Hopefully you've got a little bit of what ambipolar fields are, why they're important. I'm going to switch tacks here quite dramatically, suddenly. And I want to talk a little bit about, actually, okay, great. So you've got a scientific goal. That's the first part of my job, is you want to do science. And the second part is, okay, well, if the technology doesn't exist, can we go and invent such a thing? So before I talk about that, let's talk a bit about the sounding rocket program. Okay, so say you have an idea for a scientific experiment that needs space, and that you have a bunch of friends or yourself, you build scientific instruments, or you have friends who build scientific instruments that can be flown and built pretty cheaply. Well, then NASA launches about 20 of these suborbital spaceflight missions every year. And I've been doing so since the very beginning, really. It's sort of, you go up, you come down, and that's a feature, not a bug. And it makes it quite cheap because you have shorter space flights, but you can take a lot of hardware. You can basically build a full-size satellite, but you don't have to spend a fortune. There's not all the oversight on it. So every year, NASA actually has a competition that they open, and they welcome proposals from anybody who's got a scientific idea and they think they can pull it off with a space flight. And the cool part is anybody, absolutely anybody at all from the United States can propose an experiment. Although, of course, you need a good question, and you need to make a compelling case in your proposal that you'll be able to answer it. But it really is somewhat as simple as that. Meanwhile, I figured that we want to go after this electrical field. So this thing initially kicked off with my friend Alex Glosser and I he's my project scientist talking about this. And I went back to my office at night and started to think about and sketch out what it would take to measure this electrical field. And then I was joined by others, at Goddard, my friend Dennis Chorney. He's an instrument an instrument scientist who's quite the expert in designing these things. He helped kicked in some ideas, but basically the initial bit of Endurance was just me in my office after hours playing with computer models. And then I had something that worked beautifully on the computer. But we actually then, supported by my lab, we proposed to the sort of internal funding in NASA to try and build a prototype. So basically, we went for about 2 years. We went from a sketch all the way through to some metal with some results, and that was pretty exciting. See, this is not the whole thing. This is just a piece of the instrument and some of the electronics we might have. And you can see it's a small thing. It fits on the palm of your hand. And so here is hopefully the machine. So then I was ready to write my proposal. Crossed your fingers, and actually didn't get selected the first time. But second time, I got life-changing news in December of 2018 that my rocket Endurance had been selected. And in fact, this is at the time there was this major scientific conference going on in Washington, D.C. And that's when I got the news. So I went up to the stall there. This is the NASA stall, and the sounding rocket booth. People have a thing. I'm like, I'm a rocket PI. Can I hold your rocket up? And they were like, yes. So yeah, we had a fabulous time. And then of course the real work begins. So great. We've built something that works in our lab. We've won our proposal. NASA has entrusted millions of dollars to us. Now, getting something to work down here is very different from getting it to work up there. as I would find out, because I had yet to actually fly something in space. I've been involved in many flight projects, but I'd never actually like led an instrument that actually had been my kind of thing, and then we'd fly it. So the question is, does it fly? So my colleague Rob Pfaff, he's sort of the head, he's the project scientist for the Sounding Rocket program. He's at Goddard, and he won the remember I told you we got selected in the second round. He had won the year before, so he had a flight, a rocket flight coming from the Eastern Shore and just down in Virginia, just this last summer. And so he actually, if any of you have read, Douglas Adams, I've now become a hitchhiker to space. So we raised more funding through NASA's internal funding to take this initial kind of bits and pieces instrument and actually build a full prototype. And at this point, of course, because I had endurance funding, I had my own mission funding to bring to the table, I could help. We could pool resources and we can actually build a working prototype. So this is it here. So here it is on the table over there. You see it's got a red cap on the top. Fun fact, anything you ever see on a spacecraft that's red, take that off before it flies, or bad things will happen. They make them red so you don't leave them on. So this guy here, this is Paolo. He's the digital engineer. Basically, he designed and programmed the brain, the electronic brain of the instrument. This is Dennis. Remember, he helped a lot with the early conceptual sort of work. And then he's the guy who makes stuff work in the lab. We've been doing just a lot of work just today and yesterday, trying to get a lab set up to work. It's quite the black art. And then here, this is Long. He's the mechanical engineer, affixing the sensor to the payload. So this is the Dynamo 2 payload. This is somebody else's rocket. And you can see here's the sensor here. It was on a short boom. Just like endurance, actually, a lot of these instruments, they're kind of just like, think about like an umbrella, how when it's folded away, and then when you go up in space and you take the nose cone off, pop, out goes the umbrella and all the things fold out. And that's what we're going to do. I had been in my basement for over a year with COVID at this point. So this is now May 21. And it was very hard to try and convince myself that I really was a rocket scientist. So suddenly coming out of the basement and getting to integrate an instrument, this is fantastic. So here am I actually next to the Dynamo 2 rocket. It's a much bigger payload than Endurance. It's actually like something like 3 spacecraft. It's split into 2. It ejected a little sphere. It was really cool. It's a really cool mission. And my little hosted payload inside. And then in July, I took my family down to the Eastern Shore. I took my seat in the mission control center. It's a whole other story, but the actual day that we flew, I didn't expect to be launching something to space. I mean, now you'd think that was strange because I put something on a rocket, and that rocket had been put on the launch pad, and I'd gone to mission control, and I'd sat in a little booth in mission control, and I was like, no, we just kind of figured that the conditions weren't going to go right, and so I was sitting there. Nobody was really expecting to go, and then suddenly conditions just got great. And suddenly we're counting down, and we're like down at T-30. And I was like, wait, I thought we weren't going to go. And I was like, wait, I guess we are. So at about T-60 seconds, I could bear it no longer because we were in the mission control. There's no windows. So I put down my headset and ran up the staircase up onto the very top. So I could actually, because I'm like, if I'm going to launch something into space, I've got to see it with my own eyes. So this is hopefully what I saw.
ACS check 204.
And I hope you can hear the audio.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
And we have liftoff. Terrier burnout.
5 and 9 meter tracking off the pad.
18.
And black brand ignition.
Second stage ignition.
Just remember how big this thing is, right? You saw me next to it. So I was...
18 tracking 2.
There we go. So I was about...
Lock all TM links.
Yeah, hang on.
All TM links.
There she goes. You get the idea. The rest is just a lot of fire. And there it is.
Second stage burnout.
So I was about, 5-ish miles away from the pad, and the actual launch was behind trees. but I knew the launch time. So I just called my wife. Then like I just was counting down. And as I did on the beach in North Wales with my model, very enthusiastically counted, yelled out the last 10 seconds of the countdown. And then like initially I saw nothing, but then I saw this because of the trees, and then I saw it lifting up on the booster stage like that. And I cried with joy. And then that burnt out. And then when the main stage lit, I just lost it. It was great. And I saw this thing powering into the sky. And I got to say the feeling of, and then about then the roar of the rocket kind of hit. And if you've ever heard a rocket, I can assure you, the feeling of knowing you've built something and put it on a rocket, it feels just like it sounds. And actually, as the rocket kind of went up into space, I got quite teary and emotional because I suddenly realized, that's it. I'm now a rocket scientist. That's pretty cool. But did it work? So here's the date of the instrument went back. Don't worry, I'm not going to go through it. This is probably intelligible. This is so on the X. This is just it's graph time. The X-axis is time. So this is actually just 2 minutes of data, right? So around 1 p.m. So here we go. So the instrument basically turned on at about 122 kilometers, deployed, did its thing, did its umbrella thing, turned on as we expected, and we took data all the way up. So then you can see we sort of, we drifted up to about 130 kilometers and then fell back towards the ground. The instrument survived a lot longer than we expected to. About 88 kilometers, part of the instrument finally shorted out. And then a few minutes, a minute or so later, it hit the bulk of the atmosphere. The boom snapped, and that was it. And now, then the wreck of the rocket hit the Atlantic Ocean, and now is lying at about 3,000 feet of water. But we got a few minutes of data, which I actually this is just the science product, so I won't go into it. It's not that edifying. I actually have a paper I've submitted on the results, but mostly what we got from this was. Primarily, this was, of course, an engineering test, right? Does our experiment work? And actually, I learned a lot more from the things that didn't work as the things that did work. And we actually had enough time to incorporate a bunch of design changes, because it was then around this time, it was time to we had to start ordering a lot of the bits and pieces for endurance. So these are the sensors for endurance. So actually, on endurance, we are going to fly 8 of them just to better signal to noise. This is Chris. He's an electrical technician. He did a lot of soldering. This fine lady here, this is Tracy. She is the chief technician. She basically builds, she's the chief person who builds this hardware. She's worked on a lot of satellite missions. She worked on, I met a $1 billion flagship mission I was a part of called MMS. She built all these flagship quality missions on MMS, and all of the endurance sensors, all of her work is up to that exact standard. So she builds this which is great. So these are the 8 sensors that we're going to have. They'll be on 4 booms and a little electronics box there. So this is just some hard. So this is if you want ever going to be a rocket scientist, like this is your deal, right? It's basically you and the small team. You have your science, and then you build your experiment like this, and then you take the experiment and you mount it to the rocket. So up here, you can see here they are. This is it being mounted onto Endurance itself, into the exposed experiment module. You can see the sensors there. This is fun. This is a recognizable bit, the nose cone, right? This is the deployable bit. The gray is actually a heat shield, because this thing takes off the pad so fast that we actually need to cool it. And a fun note, so what G&K rocket yards, whenever Kirk and I would fly rockets, as a payload, we would often fly coins. I mean, it was a thing that Kirk had in his pockets, right? So I figured, well, Endurance is it's a tri-nation mission, right? So for a start, representing Norway, the Kingdom of Norway, which is our launch site. We're launching from a Norwegian range. They're supporting the facilities. I have a Norwegian krona from a friend of a friend. And then things get interesting. So this is a US bicentennial quarter, which actually Kirk, him gave to me himself. So just as he, for the rockets on the beach, well, here he is. He's giving me a coin to fly in the rocket. And this is fun. So I have a UK penny here. This penny actually was in my bedroom whilst I was growing up, and was in my father's shed for a while. So, and I found it. So I have a supply of these. So I have a penny to fly for good luck. The Romans, you see, put a coin in the mast of a ship for good luck. And they always, our flights tends to have better luck if we had a coin. So I figure what the hell? Here we are actually integrating it, the full rocket together. So you see the service module is kind of in pieces. So it's not just the rocket, and there's a whole team that NASA puts to help build the spacecraft. A whole bunch of people. I can't show them all, alas. But this is Ahmed. He is the telemetry engineer. So basically, he's the chief guy for all of the wiring and the telemetry in the service module. It's a really big job. This is Frank, who's putting it together. Yeah, Ahmed actually is. I was very kindly. I was pushing to take a camera on board because there is no scientific reason for it. But we basically, I begged NASA to let me try and fly a camera. And at the suggestion of my dad, actually, it's like, well, a cheap way to take a camera is to take like a Raspberry Pi. It says off the shelf. And we figured out that Ahmed basically we got him one of these. So for $200, we're taking an off the shelf Raspberry Pi camera, and we're going to fly that to space and hopefully take a photo. It'll be quite fun. So here's a video of the payload being hoisted. So now it's fully assembled. Now we've got to hoist it up to the vertical assembly. Here we go. This is a scary moment. And this is Norm. He's the mechanical technician. He's the guy really who's building it all together. So you can see here the nose cone's coming over. We basically putting the nose cone on in place for this testing. And here it is. So here is the fully assembled payload with the nose cone on top with our trajectory. And the final thing I'll say is that despite all of this, the test flight and all of this journey I felt that a lot of my career has been building towards, the somewhat exciting thing, if you want to call that, is I don't know if we're going to succeed, right? We think we have our best guess that we go here, we make this measurement, it's all going to work out, but there's no guarantees in rocket flight or space flight. But one guarantee is, whatever happens next May, this kid is going to be really excited to see his even bigger rocket fly. And with that, I want to thank everybody for listening to me tonight. And Go Endurance can solicit any questions.
Thank you so much, Glyn, for sharing your passion with the Hillside Club this evening, and also for sharing just this enthusiasm about rocket science and international scientific cooperation. It's a good reminder of just how important that is for community and for our world. So thank you for that. I have one actually that I put in the chat, Raspberry Pi.
Basically, it's an off-the-shelf little tiny computer on a chip, and you can buy accessories for it. They're very popular, actually. It's like, so my dad turned me onto this. He built one of these things to sort of to as a camera to monitor out his window and stuff, and for when folks are coming by. So it's like, well, there you go. Actually the technology of taking the picture isn't different. But cameras aren't difficult technology. The difficult thing is you've got to put a camera on a rocket and send it 800 kilometers away, and you've got to tell it to take a photograph, and then you've got to take that photograph and break it down and transmit it back through the rocket's telemetry system. That's the difficult bit. The problem is we cannot get it back, and we can't recover it from that high. So it's not like, we wouldn't want to. We're going to impact the Greenland Sea. It's dangerous, right? Imagine sending people out to try and recover. It's not worth it. It's too dangerous. So it's not like we can just like put like a GoPro or something. People have flown GoPros on rockets for time, but you have to get it back. And the tricky thing is here, what if you can't get it back? You better take a photo.
And with that, I'm going to turn it over to that other fellow that you just saw in that photograph. I'm going to see if Kirk McCusick would like to moderate any questions.
By all means, put your questions into the chat. We have a couple here already, besides the Raspberry Pi. And no, it's not something that you eat. How do we know what other planets' electrical fields are if we don't even know what our own planet's electrical field is? How is it that you know these other planets but you don't know Earth?
The first time that it was done was at Venus, because we stumbled on it by surprise because it was so strong there. We were able to measure it. People had an idea of the technique that you might need to do to actually measure to try and measure the thing. but I realized, but there was a piece missing. And so sort of the interesting things in science is having the thought. And I remember just like I suddenly like, looking at data from Venus and chatting to my colleague Rudy and back and forth. And we suddenly realized this is what we've been missing all this time. We just need this other step, and then we can try and pull out the field. And we were successful because it was just enormously powerful. At Mars, we've not really made an instantaneous measurement, but my colleague Shaosui at University of Berkeley, she's a very smart woman. She basically took all the data from the MAVEN Mars orbiter, all of it from this one instrument, and crunched it, and basically through raw brute statistics was able to tease out sort of an average picture of the Martian drop. But it's never been done at Earth just because the technology to measure something that small, it's not been done. And also the technique, we hadn't really refined the technique until recently. So it's this combination of we have the technique, and now we have the technology, which hopefully will work, which we'll find out. And if so, we'll go up there and we'll measure the field.
What do you think the answer is going to be? Is it going to be a big surprise, or?
I don't know. So the interesting thing is this, right? That Mars's field is very well behaved. If you calculate what it should be, according to physics, it says you should get about 0.7 volts out of it. And that's what you see. And Earth, you should predict about 0.3 volts, right? But Venus, you do the same thing. I would say at Venus, you would expect about an Earth-like kind of strength, but it's not. It's enormous. So I just don't think I would say that if you were a betting man, I put your bets on it's going to be weak. And that's an interesting clue, isn't it? Because then that is I'm not saying all that by itself is why Earth is habitable, but it's an important piece of the overall puzzle if you're trying to piece out how it all works to know where that dial is set.
Why are there no magnetic fields on Mars or Venus?
Mars's magnetic fields, Mars lost its magnetic fields. I'm not going to answer that question because I'm not up to date on all of the latest research from the InSight Mars lander. There's been a lot of the interior studies of Mars. I'm sure there's been a lot of stuff coming out. And because I've not been on top of it, because I've been busy with endurance. So I'm not going to answer that question because I don't think I'm up to date with the latest research. Venus, we don't know if it ever had a field or not, because the surface is so the reason we know Mars has a magnetic field, there are lots of rocks with iron in them. If you take a big rock, a rock full of iron, and you put it in a magnetic field, the iron becomes magnetic, right? It becomes a little magnet, and it's what's called remnant magnetism. So Mars actually still has, on the really, really old rocks, they still have this remnant magnetism, and you get this very weird, complicated, basically just magnetic rocks on the surface, very faintly magnetic rocks on the surface that you can pick up. Venus, the problem is if you take a rock and you cook it above a certain temperature, all the magnetic field disappears. It's called the Curie point. And Venus is so hot that it's heated above that temperature. So any magnetism is gone. So we just don't really know. Venus is a lot more mysterious.
I know that money is always an obstacle in rocket science, but if money were no object, could you do the atmospheric research you want to do with an orbital satellite?
The up and down is a feature, not a bug. I need the flight that goes up and comes down. You give me money is not an object, I end up right back on a rocket ship.
Why do you need to go up and down?
Think of endurance as basically like a probe on a voltmeter. So this is going to be for people who know electrics. So if you want to measure a voltage, right? You need to say like on your car battery, if you've ever done that, you put a probe on one. You have a probe on the negative, on the neutral, and you have on the positive, and you put your two probes on it, and you measure the electrical potential between them. Well, endurance is basically like the probe on it is a single probe, and what we can do is we're basically measuring the electrical, the voltage difference between where we are and the bottom of the ionosphere, basically. So, and if you're just at one fixed altitude, you're measuring sort of that drop, but you don't get the structure of it. So I want to take my rocket and I want to fly up so I can actually not just measure how strong the field is, but how that field changes as I go up in altitude. Because where that field lives is really important. And you could have 1,000,000 volts of potential, but if it's up at, geostationary orbit, well, there's no atmosphere out there to work on, right? And so it depends not just how strong it is, but where it is, where it kind of lives. So that's why I want to go up, and that's why I need a rocket, is because I want to measure the potential. So I want to measure the electrical field, and I want to measure how it's distributed with altitude.
Is it important where you're flying that rocket from, or really the point is, would Earth's atmospheric voltage be the same everywhere, or is it dependent on where you're measuring it? For example, do you have to be in a certain part of those magnetic field lines to get a particular value?
Great question. The place to me where this field matters is over the North Pole. So if you think about your bar magnet, right, with iron filings and things, if you think about that bar magnet, at the North Pole, everywhere around the equator, the magnetic field lines sort of close in a loop, right? And so if stuff escapes if ions escape, in the closed field lines around sort of the equator, they can go up and they'll come back down. They will follow the magnetic field lines and they'll rain down onto the atmosphere and they won't escape. But if it's the field lines at the poles, which are important, because those are basically the highways to space, right? That is, it's there and only there that, around that place where where those field lines open up to, and those connect all the way out into the solar wind. So that's the passageway that stuff can escape. So that's why I'm going to Svalbard, because I want to launch vertically into those open magnetic field lines to actually measure the field where in the place where it's causing the escape.
That's implying that the voltage isn't necessarily the same everywhere around the Earth's atmosphere.
At the poles, there's a bunch of other stuff. You get precipitation from the solar winds. You get electrons coming down. That can change the equations slightly. So you actually probably would get you would probably get a different potential drop over the pole as you would at the equator, because you don't have that rate, because you have all that electron precipitation. So yes, I think it conceivably may be different.
Okay, so ask the question slightly differently, which is what's going on in chat. What establishes a planet's electrical field?
If you've ever done what you shouldn't do with a bottle of champagne and you shake it up and you pop it up, right, the pressure inside pushes basically all the champagne out, right? So you have pressure here, which is pushing the stuff out. This is going to have to get technical, and there's just no other way around it. So here the deal is this. This only works, so remember I said the top of the atmosphere, it's broken down, it's a soup of ions and electrons, right? So all these ions and electrons. And remember that the electrons are negatively charged and the ions are positively charged. And in general, if it's just sitting there, all the charges will basically balance out, okay? But now at this pole, basically the electrons all by themselves would happily escape to space, just because there's so much pressure, they have so much thermal pressure, they're so hot that just like the champagne, they would happily escape off those open field lines out into space. They would just be gone. But they can't, because they're sort of shackled to the ions. If you think about the electrons are trying to leave, as they pull away, this electrical field is forming to bind from the ion. Basically, the ions are pulling back on them, right? And that's what the ambipolar field sort of is. It's why it's called ambipolar, right? It's in both directions. So the electrons are pulling out, and the ions are pulling this way. So basically, this field is forming to slow the electrons down. But in the same way, it also helps pull the ions out. So that's basically what we think causes it.
So the Earth's magnetic field reverses periodically over the Earth's history. What cumulative effect does this have on the overall atmospheric protective effect?
So the periods of the reversal is, in geological times, it's pretty quick. It will be pretty exciting if it happens, if you're around and that happens. It would be pretty exciting to see what happens, I think. But the Earth's field, it has this cycle, just as the sun has a cycle, but the sun's is much, much quicker, right? So I think that we can have, I don't know if people have modeled it or looked at it. I suspect they have. It's a good question.
Could you, for example, put your instrument on something like one of the SpaceX missions that's going up to the space station and back? Because you that would take your instrument up and down on a longer period of time, but it would give you a greater amount of space that you would go through.
Well, alas, space station is about 400 kilometers. And that's sort of the beginning of where, actually, you could maybe measure something there. But remember, I want to go to 800 kilometers. And I want to go over the open magnetic field lines at the pole. And that is, the space station doesn't go anywhere near it. So alas, no, again, it's, give me all of that. It's rockets, it's sounding rockets all the way. And of course, I couldn't take all of the other stuff with. You can take a lot of kit to the space station, but it's a different thing. The mission doesn't call for it, right? The science, I mean, that said, however, there are really cool stuff you can do on the space station. Actually, Alex, my friend, he who helped me, concoct endurance, he has actually just became the PI of an experiment that's going to fly to the space station, and exactly like that, it's going to fly in the Dragon trunk, and it's going to be mounted onto the station. And so he's got all kinds of cool stuff. But the science just doesn't dictate that. It wouldn't be useful to me.
So obviously things then like Blue Origin or Virgin don't go anywhere near high enough.
No. I mean, fun fact, I remember we kind of had a joke, like, so the day that Richard Branson launched to space, 80 kilometers is no. There's a good, I mean, where does space begin is a good question, answerable question, but I don't think that any, some people will argue 100 kilometers, but I think you might call it sort of near space. The same day as, we launch, past, the common line into sort of highest actual space, or as we in the space business call it, space. So Blue Origin, actually, so the Blue Origin one goes higher. It flies to like 100 kilometers. I mean, that's still a little low for the science I want to do. This all said, however, there are lots of people out there who want to do microgravity experiments. And there's lots of cool science you can do on suborbital vehicles like that. You can't do my science, right? But you can do great like microgravity experiments, especially in a Blue Origin. It's a long flight. You go higher, you get more time. There's cool. It's not for me. Just to remember. So when on the test flight that we launched for Dynamo Rocket, I showed you, and we've got to 130 kilometers. And what I didn't tell you is there were actually 2 Dynamo 2 rockets that were launched. There were 2 of them, and we were only on one of them. And it's a good thing because they were basically identical. And just the luck of the draw of, I told you they're unguided. So the altitude you get is kind of, it'll be somewhere between here and here. And essentially, if we were going to, if we'd been on the other rocket, it would have gone 120 kilometers. Nope, would have seen nothing. And we just lucked out, and we're on the one that went to 130, and we got just perfectly positioned to take our science. So my science needs to go higher, but you can still, I don't want to disparage, you can still do great science from those suborbital vehicles, especially with reflights. If they can get to the point where you actually can do quick turnovers, then it's a very different deal.
Presumably balloons aren't going to get you high enough because they're not even out of the atmosphere.
No. Actually, NASA has a balloon program. Same deal. Anybody can propose to that too. People do great stuff with the balloon program. It's also based out of Wallops.
So what kind of science do the other missions that launch from the Svalbard study? It seems like an expensive place to launch if you don't need to launch from there.
Svalbard is perfectly positioned. The reason there's a launch base there, so it's part of the Norwegian launch range. It's perfectly positioned if you want to look at, so we're going there because we want to basically head towards magnetic north and look at the open field lines. It's kind of unusual, actually. Most people are there because they want to really study the aurora. And it's just perfectly positioned over the auroral arc. That's great for launching into the aurora. There's also fabulous radar on Svalbard and around. It's a European radar, which is also supporting endurance. Actually, the Brits, this is why we have we don't have the British flag on the mission patch, because I'm originally from there. We have it because they're a co-I. So Susie Imber of the University of Leicester, she's leading the IceCat radar team. So it's this combination of they're perfectly positioned to look at auroral precipitation and the auroral arcs. You can fly a rocket right into one of those. You've got great radar, and they have the range.
Test instrument was on a launch, and now your upcoming launch is going to have the full instrument. Is there any other follow-on that you plan to do after that? Or is this just a sort of one thing and then see what you get and maybe propose something else later?
I'm kind of like one at a time. You know, we'll see how it goes. Right? I think we'll see what we get, because the other fun thing is my next launch window to do endurance doesn't open until about 2028. So I have in order to even think about making this measurement, we really want to launch, at least initially, we want to try and do our launch in the quiet part, the solar, that basically in solar minimum. You know, the sun has this 11-year cycle. Well, we're very much on the ramping up towards solar maximum, but we're just inside this. So really our next best window doesn't open until 2028. So fingers crossed it works.
So why do you have to do it at that low point?
Well, when the sun gets more active, it can heat up the atmosphere and there's more collisions, and the primary measurement basically it can stop the technique that we want to use from working. Basically, you can get the neutral atmosphere puffs up, and it can stop the technique from working.
Just to consider an extreme, what's the EMF situation around the sun?
I don't know, but a similar deal is going to occur because you have this big electron pressure. Although there, of course, the ions are mostly hydrogen, right, or protons. So you have this you have probably a big pressure gradient on there. I don't know. I'm sure it's been worked out. It's probably part of solar wind formation. Again, I'm not a solar guy. You need somebody. I'm not a solar heliophysics guy, but I know many of them. I work with them.
Just to wrap up before I turn it back to Arlene, first of all, from Robert Kennedy, who's another rocket scientist, great talk. I enjoyed it and learned a lot. And from one of our members, Glyn, this talk was fantastic, and you geared it so well for various levels. Your enthusiasm and fun with all this is infectious, and we just want to thank you a lot. I know Earth and some science as well as Earth and space now. Thank you.
Well, thanks very much for having me.
Let me thank Dr. Kirk McCusick for moderating the questions. It was a pleasure to see the two of you together as adults, the beginning of Glyn's career as a rocket scientist. So that was quite lovely, really. So thank you so much for coming this evening. And tremendous thanks to Dr. Glyn Collinson for sharing his passion and a lot of terrific information.